Okay, I'd like to talk here, okay?
Yes.
To see my slides. And which is for what?
Laser.
This one read. Oh, thank you. This one read. And okay. Okay, thanks very much. The invitation to this interesting conference by Marco, my old friend. Okay, I talk on these highlights of the Calet observation over 10 years. And my name is Shoji from Waseda University of PI of Calet. And at first, I was very afraid about that. My talk could not be understood without any introduction of cosmic rays of the Gambari bus. However, this Roberto and Maria could have a very good introduction of both. So I am very relieved to show my slide now. Okay, so this is Calet is launched in 2015 by Japanese rocket and impressed on the Japanese experiment module number 9 here. And this Calet overview of missions. Calet composed of the main detector of calorimeter and also the gamma ray burst monitors. And this is the specific of the Calet payload. And this is a Calet collaboration. Calet is collaboration with Japan, Italy, and United States. And these are PI of these each countries. And this is an Italian institution to be contributed to the Calet. Here is the name of institution, and the main contribution is here. This provided by PL or PI of Italy. And this is a history of this Calet collaboration between Italy and Japan. This is some graduate to the ASI for the Calet missions, and this is some of the press release and congratulations to the successful launching at the Tanegashima Space Center. Especially, we thanks to the contribution of Professor Guido Castrini and Sergio Ricciardini from IFAC by providing us a state-of-art high voltage system by via ASI, which is operating without any trouble over 10 years. Okay, this is schematic side view of the Calet calorimeters. Calet calorimeter composed of the charge detector, imaging calorimeter, and task from the top. And charge detector measures the charge from Z equals 0, that is gamma rays, up to the Z equals 40. And imaging calorimeter has capability to measure the shower imaging as the first stage of shower, and total absorption calorimeter measures the energies. And in total, the thickness of calorimeter is 30 radiation lengths. It's consistent to the atmospheric depth. So this very ideal space experiment to observe this cosmic ray and gamma rays in space. And this is a picture of CHD and task, and this is CHD IMC and task. And this is the element of CHD, which is composed of the plastic scintillator and the PMT, and this is IMC, consisted of the scintillating fiber and multi-anode PMT, and this one is task composed of the PWO scintillator and read out by APD-PD. By these detectors, we can observe this kind of example of Calet. This one is a proton candidate, and this one is a gamma ray, electron candidate and gamma ray candidate. These are distinguished by the existence of charge at the CHD. Gamma ray has no charge at the top, but electron has same charge, absolute number 1, and very similar shower development. And this is proton event. Proton events could be identified from the electrons. Since calorimeter has no capability to separate the charge sign of particles, we cannot distinguish -1 charge and +1 charge. Therefore, this discrimination of protons could be just done by this shower development in the task. And the ion, this is ion result. Ion is identified by the charge at the top of CHD. And this is the charge resolution, which is observed by the cell beam test here. And this one is IMC, and this one is CHD measurement. And at higher energies, CHD capability to measure charges becomes less. Since these backscattering particles could someday have contamination of charge. Therefore, we are using at higher energies in the IMC charge resolution. This is a readout of the energy, a measurement of energy from the 1 MIP to 10 to 6 MIP. This is very wide dynamic range measurement of energies carried out by the four-type readout of the PWO signal. One is APD, low gain, and high gain, and PD, low gain, high gain. By these 4-channel readout in different ranges of energies, we can cover these very huge regions from the 0.1 GeV to 100 TeV per log. And this is energy resolution. And energy calibration itself could be done by the accelerated experiment, also this rigidity cutoff effect. And this right figure shows some of the energy resolutions. For electrons, the energy resolution is much better, less than 2% above 20 GeV. For hadrons also, this energy calibration was done by serum SPS by using the fragment of iron. And linearity assessed up to 6 TeV, and energy resolution for hadron shower is around 30%. Okay, this is performance of the Calet energy measurement over 10 years. So we have the two types of triggers. It's one is a 10 GeV trigger, high energy trigger, and one is 1 GeV, low energy triggers. And for high energy triggers, the lifetime fraction is 86% as shown in the figure, and exposure factor for high energy is around 320 square meters per radian day. And this plot shows this task energy deposition from 1 GeV to 1 PV. As I mentioned, it covers 6 orders magnitude of energy measurement by single instrument. And with a high energy trigger, this energy spectrum is very smoothly power law up to 1 PV. It means we have no saturation in measurement of energies. And from now, this I will show you some cosmic observation results. This is a cosmic electron results. So up to 1 TeV, our result is very consistent with MS. However, there is some systematic discrepancy between this Calet MS and to the Dampe and Fermrat. And at TeV region, we expect some softening of energy spectrum, and it is caused by the energy loss during the propagation, as expected by theory. Then we have, in fact, we have some results to show this steepening of spectrum is here with a significance of 7 sigma. This is a highest energy observation up to 7.5 TeV by Calet as a direct measurement. And this is some model fits with the Calet results with AMS positron fluxes. As you can see that in the low energy region below 1 TeV, Calet electron plus positron result and the AMS positron result could be understood by the contribution from for supernova remnant electron contribution and also pulsar contributions. But for the high energy region, it is not understood by these models, and we need some nearby sources like this Vela, monogem, and so on. And of course, in addition to the astrophysical sources, the possible contribution of dark matter is investigated. If dark matter exists at some fixed mass, it contributes to electron and positron like this. It's not power spectrum. And then we can see the sum, we can see the sum, the excess of the electron plus positron fluxes. By this techniques, now we are getting the upper limit of annihilation and also decay model. And this is new result of the measurement of dipole amplitude of arrival directions. If there is some effect of the nearby sources like Bella, we can see this kind of dipole structure. Okay, then we measured this dipole amplitude with the black lines, and thick red line shows 1 sigma error to the random distribution, and the thin red area is 2 sigma area from the deviation from the random distribution. And then now we can see the sum the what is the arrival direction at over 1 TeV. Here is a 1 TeV, and this result is very consistent with random distribution of sources without very consistent with random distribution. And here is the arrival direction of electron. Here is a Vera. However, if this threshold is increases to TeV, the amplitude is somewhat increase and within 2 sigma region, and also this is arrival direction. And this one is 3 TeV, this one is 4 TeV, and finally the 5 TeV, 14 events show this highest dipole amplitude debated about 2 sigma. It's not significant, but dipole direction is very near to the Vera region. Okay, so from now this I talk on this heavy cosmic ray element from proton to nuclei. The proton to nickel is somewhat accelerated by the supernova remnant by generation of shock wave. And this is a cosmic ray abundance observed by Calet from hydrogen to the nickel. This was observed. At first, I'd like to talk on the proton spectrum. As in the introduction of Roberta, the cosmic spectrum is single power law. However, now clearly the proton spectrum is deviated from the single power law, and we have seen some hardening of spectrum over few hundred GeV, and again the softening and 10 TeV region. This is spectral index changes. And also helium spectrum is observed from the 40 GeV to 400 TeV. And also it has a very similar structure with protons and hardening and softening observed. And we compare this proton and helium spectrum in rigidity. Then you can see this softening and hardening region. So hardening and softening region are very consistent in rigidity. And this is a proton-helium ratio, and the spectral index of helium is harder than that of protons in the full rigidity region. It means that helium becomes dominant at the higher energies. And still that over 10 TeV, we have some discrepancy from single power of this proton-helium spectrum. But it should be carefully checked. It could have some implication of very dominant sources. And this is some the cosmic ray spectra from carbon to iron. This is a result of Calet observation. We observed this main component up to the 100 TeV, and this is the charge resolution of each charge region. And this is all particle spectrum calculated by assuming the ratio of element observed by Calet. And you can see this reaching to the near to 1 PV. And now this we can compare with our result with a ground experiment. And this is, we can see some the structure of spectrum. Here is hardening and softening also in all particle spectrum. From here, I will show you the each component carbon and oxygen has some, it is measurement of carbon and oxygen. We have some systematic discrepancy with AMS in the absolute fluxes. However, the ratio is very consistent. And carbon and oxygen has also some similar hardening comparing to the proton and helium, like here in the similar energy region. And this is a boron result. Boron is a secondary particle produced by the carbon and oxygen in space, and the boron is secondary. So this power index of spectrum should be softer than the carbon and oxygen. It's really softer. However, it's also similar hardening at a few hundred GeV. Nitrogen is coming from the primary or secondary origin. So it is, as expected, its spectral index is between the carbon, oxygen, and boron. And this is a boron-carbon ratio. Boron is a secondary. So it has some information of the propagation cosmic rays in the galaxies. Up to a few hundred GeV, this spectrum is a very single power law. However, at the higher energies, it has some soft hardening, flattening. It is understood by leaky box model with some residual motility around supernova remnant. Okay, so this is it's hidden by. However, this one is a combined analysis, carbon, nitrogen, oxygen, and this combined analysis shows also the spectral hardening and softening inconsistent with the proton and helium. It indicates some the effect of acceleration limit of supernova remnant. And this is nickel energy spectrum and also nickel to iron ratio. As you can see, nickel to iron ratio is very, very constant in all energy range. It means that this nickel and iron have a similar behavior. And this one is sub-iron fluxes. Sub-iron measurement was not done so much. So this is first result at the higher energies. We compared the sub-iron spectrum to the other low energy experiment. Sorry, like this. And this one is a sub-iron ratio. Also, sub-iron secondary, it should have some information of the propagation. However, this case is simply simple spectrum without any break up to a few hundred GeV. And in addition, we have some special trigger mode for ultra heavy cosmic rays. It means heavier than the iron. Since this iron and nickel could be generated in the nuclear fusion in the massive star. However, over nickel, it could not be produced by the nuclear fusion process in the massive star. Therefore, the ratio, the number of fluxes suddenly becomes less. And this is elemental abundance normalized to the iron is equal to 1. And these results are very consistent with other super tiger and ace abundance. And this is a gamma ray measurement in GeV regions. Our detector is much smaller than the film. However, we have the gamma ray map, sky map here, and this is individual sources. And for the strong individual sources, we have some energy spectrum consistent with Fermi, and also diffuse gamma rays up to 100 GeV measured. And this is gamma ray burst, and it was also introduced by the Maria, and we have also the short burst and the long burst here. And this was the charge sign dependence of the solar modulations. This is some counting rate of the electron and protons from the beginning of observation for 10 years. The observed different behavior electron and proton is consistent with expected charge sign dependence of solar modulation, which is reproduced by the numerical drift model of cosmic ray transportation. Also, we are measuring all the what we should decrease here. Okay, so by using the CHD count rate, it's a measurement of MeV electrons. We observe sometimes some very rapid increase of this count rate. And this count rate called, this kind of phenomena is caused by the relativistic electron precipitation rep event. It is the whole of the relativistic electron from the Van Allen belt. And this should be caused by some electromagnetic wave, and we discovered 3 types of rep event caused by different kind of electromagnetic wave related solar activity. It contributes to the space weather measurement. This is my summary, and also especially the extended operation approved by JAXA through to the end of 2030. And next, I will talk on the our future project. Yes. Okay. Thanks. This is my slide, and this is a current. So now we are discussing for some future collaboration between Italy and Japan. It's proposed by the Pier Simone in Italy, and this is a high-energy cosmic ray radiation modular telescope on the moon. It's called the Moon Ray Concept. Okay, it is a station on the moon, and this detector is modular detectors to build easily, and this has a very big